Hello everybody. In this video, we'll learn about partial derivatives. Those are derivatives of multivariable functions, which are very similar to ordinary derivatives. There's just more of them, as we'll learn later on in this video. To begin, let's review what happens in Calculus 1. When we calculate the derivative of a function, df dx, you can think of that as the change in f as x changes by some small amount. We might visualize that with something like here. Here's a graph of a function f of x, right? And let's say we want to calculate how we're changing at some point x. So what we'll typically do is we'll calculate a ratio of the change in f over the change in x. We'll start with some point x, and then we'll add some small amount to it to get a new point, x plus h. So h represents the amount of change in the variable x. Right? Corresponding to x, we have the y value, f of x. Corresponding to x plus h, we have the y value, f of x plus h. So the change in f over the change in x, we can represent that as the quotient of these two changes, f of x plus h minus f of x over x plus h minus x. And we want that change to be small, so small it's infinitesimal, as they say in calculus. And for that reason, we take the limit as h goes to 0. Now this expression you can simplify in one key way. You have an x minus x, so in the denominator those cancel, leaving you with just the factor of h in the denominator. Now, of course, we can't just plug 0 in for h right away, because if we do, then on the top we have f of x minus f of x, which is 0, divided by 0. And 0 divided by 0, that's indeterminate. So we'll always have to simplify this expression first to figure out what a derivative is. And you did a lot of that in Calculus 1. Now, in our course, we have a function z, which is a function of two variables, x and y. In other words, there are two variables which can change, which leads to two derivatives. Right? Each one of these derivatives tells you about how the function is changing, but each derivative on its own only gives you part of the picture. So each one is called a partial derivative. And so we can have the derivative of the function f with respect to x. Right? How much does the value of f change as x and x alone is changing? Just like with our previous picture, right, we're going to calculate this quotient. In this case, we have f of x plus h, so the amount of change h is being added to x and only x. So we have f of x plus h comma y minus f of x comma y, all divided by h. And that's the definition of the derivative of f with respect to x. We could also call it the partial derivative of f with respect to x. And typically, you'll see these curvy d's used instead of the regular d's. And I imagine this is just to indicate to the reader that this is a partial derivative. And it's also very important when we do multivariable derivatives that we always have to specify the variable that we're taking the derivative with respect to. So we won't really see the f prime notation very often, because if someone writes f prime of x comma y, which is the variable that's changing, that notation doesn't really communicate it. So for partial derivatives, we'll typically see this notation. Again, for this derivative, notice that nothing's happening to y. There's no change in y. Think of y as being held constant. Similarly, the other derivative that we'll be interested in is the derivative of f with respect to y. And that looks similar, except in this case, since we're measuring the change in f as y changes, that plus h is attached to the y, not the x, in this expression. And from these definitions of the partial derivatives, you can actually calculate partial derivatives directly from the definition. I'll show you how to do that on this slide, and then I'll explain how actually the derivative rules you already know can be used instead. So for our example function, let's consider the multivariable function f of x comma y is equal to 5 times x squared times y. Now to calculate df dy, the partial derivative, that's the limit as h goes to 0. Division by h, I'll write that as multiplication by 1 over h, just to save some space. It's 1 over h times this quantity. And so, in this function, right, we'll have f of xy as this last part, so minus 5x squared y. Here, f of x plus h comma y, we're going to substitute x plus h in for x. Right, so this first term becomes 5 times the quantity x plus h squared times y. And if you were to expand this out and then distribute through the 5 and the y, in this first term, you'd get this expression. The limit as h approaches 0 of 1 over h times the quantity 5x squared y plus 10xhy plus 5h squared y minus 5x squared y. This actually simplifies very nicely, as all these problems do. 5x squared y and minus 5x squared y, that first and last term cancel. Every other term contains an h, so we can cancel one factor of h with this fraction 1 over h. That leaves us with this expression. The limit as h goes to 0 of 10xy plus 5hy. Now as h gets closer to 0, the second term gets closer to 0, or informally, you think of replacing h by 0, and this term disappears from the calculation, leaving you with 10xy. So this partial derivative of 5x squared y, partial derivative with respect to x, is 10xy. Remember, during this calculation, y was being held constant. In fact, you can almost think of y as being treated like a constant. Right? If this is 5x squared y, right, if this y wasn't here, the derivative would be, well, the derivative of 5x squared would just be 10x. Right? Keep that in mind. We'll return to this idea shortly. To calculate the partial derivative of f with respect to y, again using the definition of the derivative, you would start out with the definition of the derivative. Again, instead of division by h, I'm writing this as multiplication by 1 over h. This is equal to the limit of 1 over h of 5x squared, and then the y is now replaced with y plus h. That's times the quantity y plus h, minus f of xy, that's minus 5x squared y. And in this case, you can distribute that through. And again, the 5x squared y and the minus 5x squared y, those are going to cancel. The 1 over h cancels out that h. And you're left with the limit as h goes to 0 of 5x squared. But in this case, there's no h to get smaller, so the answer is just 5x squared. Right? The derivative of the function 5x squared y, the derivative with respect to y is 5x squared. And again, in this problem, y is our variable and x is being held constant. You think of x as a constant. Well, if x is a constant, you can also think of x squared as a constant. Right? And again, another way to think about this, which will become even more clear on the next slide. Right? If we're calculating the derivative with respect to y, 5x squared is like one big constant. And the derivative of a constant times y is just that constant, 5x squared. And that's how you calculate partial derivatives from the definition. So the main idea I want you to take from this is that when you're calculating partial derivatives, one of the variables is changing, and the other variable will behave like a constant. And when you're calculating partial derivatives, that's very similar to working with constants as you did in calculating derivatives in Calculus 1. So here are some examples from Calculus 1. Let's say I have the function f of x is equal to 8 times x cubed. Well, the derivative of a constant times a function is equal to the constant times the derivative of that function. All right, so the derivative is 8 times 3x squared, which is 24x squared. If you had seen a problem like this in Calculus 1, f of x is equal to c times x to the fifth. Well, c is a constant. The derivative of this function is c times 5x to the fourth. Right? And we might rearrange that to 5c x to the fourth. Right? So this variable is representing a constant. Now, here's a strange looking function. F of x is equal to pi cubed times x squared times 5 plus 7 to the fourth. We normally wouldn't write a function like this, but it is still a function that you could take the derivative of using your Calculus 1 skills. Right, in this case, see right here we have x squared times a constant. It's kind of weird because part of that constant is to the left of x squared and part of the constant is to the right of x squared. But it is still x squared times a constant, so the derivative is 2x times that constant. I just left those parts where they were. Here, plus 7 to the fourth, there's the derivative of 7 to the fourth. You might be tempted to say 4 times 7 cubed, but no, that's a classic calculus professor trick. The derivative of 7 to the fourth is 0, because 7 to the fourth is a constant. It's not changing. The derivative of any constant is 0. That's where the plus 0 comes in. Now, admittedly, we would probably rewrite this and gather the numbers and combine them in front, followed by the variable. So this would look more natural, perhaps, as 10 pi cubed times x. But think about the process that we used in this expression. Right? And keep in mind, right, the difference between multiplying by a constant and adding a constant when it comes to calculating a derivative. All right. So let's take a look at some multivariable examples. And again, I don't want to use the definition of the derivative. I suppose you can if you have a lot of extra time, but these expressions can get very complicated, especially if the exponent gets bigger. It's more complicated to use the definition. So let's use things that you know from Calculus 1, like the power rule and the product rule, to make calculating these more straightforward. So the function x cubed plus y to the fifth. If we want to calculate df dx, this indicates that x is the variable and y is a constant. Right? So visualize this function as x cubed times a constant. The derivative of x cubed times a constant is 3x squared times that constant. That constant just happens to be y to the fifth in this case. And it's really no different from the previous slide where we had the constant c, or the constant pi cubed, except this time the constant is y. Again, it's only a constant in the context of this calculation. In theory, later on you could plug in values for these if you wish. To calculate the partial derivative df dy, right, in this expression, x cubed y to the fifth, now we think of y as a variable and x as a constant. Right, so here we have the derivative of a constant times y to the fifth. Well, the derivative of a constant times y to the fifth is that constant times 5y to the fourth. So this is the partial derivative with respect to y. All right, see some more. What's the function f of x comma y? In this case, the function is 7xy plus x squared plus y cubed. Again, we want to calculate both partial derivatives. Calculate df dx. Right, so first, think of x as your variable and y as a constant. The derivative of 7xy, and 7 and y are constants, so you have a constant times x. The derivative of a constant times x is that constant, in this case 7y. The derivative of x squared, with respect to x, is 2x. The derivative of y cubed, remember, with respect to x, y cubed is a constant, and the derivative of a constant is 0. So this is the partial derivative with respect to x. The partial derivative with respect to y, so now think of y as the variable and x as the constant. The derivative of 7xy, y is the variable, x is a constant. This is a constant times y. The derivative of a constant times y is that constant. The derivative of x squared with respect to y, that's the derivative of, again, a constant, which is 0. That doesn't appear in this answer. The derivative of y cubed with respect to y is 3y squared. So this is the partial derivative with respect to y. All right, one more, a little bit trickier. I'm going to add a trig function in here. F of x comma y is equal to x times sine of y. Right? Remember, the derivative of sine is cosine. Okay, first let's calculate the partial derivative df dx. So x is a constant. Sorry, no, wrong. X is a variable and y is a constant. And so x is a variable and y is a constant. Now, if y is a constant, then sine of a constant is still a constant. Right? So when calculating df dx, right, this becomes x times a constant. What's the derivative of x times a constant? It's just that constant. Right? So df dx is sine y. What about df dy? Well, now y is the variable and treat x like a constant. What's the derivative of a constant times sine y? Right? The derivative of a constant times a function is the constant times the derivative of that function. So it's the constant x times the derivative of sine y, which is cosine y. And that's how you calculate partial derivatives without resorting to the definition. Now, functions can get a little bit more complicated. Sometimes you'll have to use the product rule. Sometimes you'll have to use the chain rule. I'll never do a problem where you have to use the quotient rule because I never liked that one either. But here we go. Here's a function f of xy is equal to x times sine of xy. Okay, so you can see from the setup that this might require both. We have a function times another function. We have an x times a trig function. So that might require a product rule. And we also have sine, but within the sine we have x times y. So a function within another function. So sine, we might need to use the chain rule. So first, let's use the product rule to calculate df dx. Right, so we have a function involving x times a function involving x. That's a sign we need to use the product rule. So that goes derivative of the first function times the second function plus the first function times the derivative of the second function. Now the derivative of this part, now the chain rule kicks in here. And because x is a variable and y is a constant, what do we have here? We have sine of x times a constant. The way the chain rule works, we do the derivative of the outside function first. So cosine, and we keep the interior function the same, x times a constant. Then we multiply by the derivative of the inside function. And what's the derivative of x times a constant? The derivative of x times a constant is that constant. And so it's very important to recognize that we need to use the chain rule in this case. All right, and that's the partial derivative df dx. What about the partial derivative df dy? Well, in this case, we make our lives a little bit easier by recognizing we don't actually need to use the product rule for this. right? Just because there's multiplication does not mean a product rule is necessary. We use the product rule if we have a function of y times a function of y. This first part is not a function of y. In fact, we have a constant times sine of a constant times y, right? So this isn't too bad. The derivative of a constant times a function is that constant times the derivative of the function. The derivative of sine xy, again, we need to use the chain rule, and keep in mind that y is our variable and now x is our constant. Cosine of x times y, cosine of a constant times y. We've got to pull out the factor of x here because the derivative of the constant times y is that constant. And so this is the partial derivative df dy. And we have an x here and an x here. It kind of looks more standard to group those two x terms together, and we do that here. So this is the partial derivative with respect to y. Now, I'm a big fan of the expression you learn math by doing math, so I'd like you to try and practice calculating some partial derivatives. So here, we have the cosine of the quantity x cubed plus y to the fourth plus x to the fifth. And I'd like you to calculate the two partial derivatives, df dx and df dy. As a little bit of a hint, you're not going to need the product rule for this one, because you don't have the product of two functions. However, you will need to use the chain rule. All right, it's a good place to stop this video. That's your introduction to partial derivatives. Thanks for watching.